Okay, definitions of derivative. Derivatives are tangent lines, but what is a tangent line? I'm going to zoom in here. There we go. Thank you, touchscreen, for listening to me. So first of all, we start with a secant line. A secant line is a point, or is a point. A secant line is a line that goes through 2 points on a curve. And when we look at this picture right here in figure 1, it's showing that we're trying to create a tangent line at point P to the graph of this function. To find that tangent line, we're taking second point Q and looking at the secant line and then moving closer, look at the secant line, move closer, look at the secant line, and continue to move that Q closer and closer. If I do that, then the limit as Q approaches P is the tangent line if I am looking at the limit of the secant line. I've got a fun little Desmos thing ready to show you. And I need to remember to put this as a link for you guys if you want to play with it. You can have A play and go through different points, or you can move it manually to where you want. And then H is actually the horizontal distance between these 2 points. This is point Q. I'm going to manually just move point Q to show you this secant line. And when I get really close, it basically looks like the tangent line. But for the program that this is using, if I actually reach the tangent line, it's going to disappear because it's having a divided by 0 problem. Slope is undefined. And now I'm moving both of them, so that doesn't work. There we go. So you can always play with that on your own if you want to. And then we're going to look at 2 definitions. This is the first definition. These definitions are very, 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 very important. And then it will allow me to draw. To point out to you this slope definition over on the figure on the left. A is the x-coordinate of the particular point we're trying to find the tangent line for. Q is a generic point based on the variable of the function. You know that slope is the change in y over the change in x. So, I'm going to do attendance by quiz. So yeah, don't worry about it. And I'm not going to mark you tardy. I haven't been dealing with tardies because I know there have been a lot of Wi-Fi problems for people. And it's just not worth my energy, to be honest. So this formula right here, you can see the change in x. And then I'm going to undo that and focus on the change in y. And just to point it out, f of x is a generic y coordinate. F of a is the y coordinate when x is equal to a. If I don't have limit, so if I'm just going to temporarily cross it out, and then I'm going to erase it. If I don't have limit, then this is the slope of a secant line. The limit causes it to go from being the slope of a why can I not speak? Secant line to the slope of a tangent line. This definition is in your textbook. If you have not had enough time to write all this down, these are clips from your textbook in section 2.7. And I'm going to move, and we're going to do an example. We're going to find a full-on equation of a tangent line to a parabola. And you know what? I learned my lesson from the last class. I'm going to change this point because I'm trying to make sure that I get different numbers. So I want to look at equation of the tangent line to y equals x squared at point 3, 9. I need to find slope. To find the slope of the tangent line, I'm doing the limit as x approaches a, where a is 3. Let me just make sure you see that. And then the definition has the numerator as f of x minus f of a. This is f of x. F of a, actually let me do a highlight on that, is actually already given to us. And then in the denominator, x minus the number a that we are using. And now you get to find out why we solved some of the algebraic limits that we had solved. I'm going to emphasize that this is now our focus. In your homework tonight, you are going to be using limits to solve slopes, derivatives. Know that if you happen to already know some formulas for derivative taking, you cannot use them in chapter 2. You have to use these limit definitions while we are in for 2 days. For 2 days, you've got to use the limit definition. It's a rite of passage in a calculus class. Maybe think of it that way. So, you know how to solve this limit. And I gave you a little bit of a head start in case you wanted to try, and I see a lot of yawning. Oh, nowadays, when you see me looking this way, I'm looking at you, even though it feels like now I'm looking at you. The awkwardness of online. You're going to factor. You see the 0 over 0 problem. We all know what we got to do to that. Die. I am still writing limit. Do not stop writing limit until the moment you are actually solving it. And in this situation, solving it is by direct substitution into the new function who has the hole filled in. Whereas if you graph the function, if you graph this function, you're going to get the line x plus 3 with a hole at x equals 3. This just fills that hole in. So we have 6 is the answer to slope when we directly substitute that 3 in. For equations of lines, you really, really, really want to use, okay, I'm just going to move to the right then if you're not going to let me do that. if we're writing equations of tangent lines, or just equations of lines in general on the AP exam, you want to use the point slope form. The point slope form is y minus y coordinate being equal to slope, and I'm going to come back to that, times x minus the x coordinate. And slope, whoop, okay, you go over there. It's not letting me write because of that. And I need you to maybe go select that. Okay. I think I'm having lag issues. There we go. Maybe it just, you know what? It wanted a different color. Oh, no. Now, this right here is the prime symbol. And you say f prime of a. It means the derivative of the function named f at the x-coordinate a. Or, in other words, the slope of the graph of f at x equals a. We have all three of these numbers because we already had that the point we were using was x-coordinate 3, y-coordinate 9, and the slope, I'm just going to write it as m to be able to write it a little bit faster. And then it's just fill in the blanks with the three numbers. When you sit down to take the AP test, hopefully not in your home, you will not do anything after you have written that. I want you to see that you did not do any arithmetic other than having to solve the limit. But once you found the slope, you just plug numbers in where they needed to go. Stop it there. On the AP exam, you do not have to write your answer in any particular way unless they tell you to write your answer in a particular way. This is an equation of a line. Leave it. If you feel the need to write mx plus b form, you run the chance of making an arithmetic mistake, which you have done and will continue doing throughout your life. Don't run that risk. When tangent line shows up, not if, when tangent line shows up on the AP exam, it's finding the slope with whatever situation they give you might be worth 1 point, and then your tangent line is worth 1 point, and a 15-minute 1 out of 6 problems is worth 9 points. If you mess up your arithmetic, that you lose the 1 point that you got for making this tangent line, and I need you to understand how important that 1 point is. When you have half of your test is free response, 6 problems, 9 points each, this is 1 point. Don't mess up the points where you know you can get it right. All right, that was my little speech about the AP exam. And this is a clip from the textbook, but I want to use Desmos because we can. I'm going to just hide that line, and let's see. Does that look like this right here? Does that look like a particular curvy spot of the graph? Right here? Does that look fairly curvy? No? Yes? Maybe? Okay. I'm going for it anyway. I'm going to zoom in on this point. As I zoom in, what do you notice? And remember, I'm recording, so. If you, yep. As I zoom in, it becomes straight or starts looking like it's going to be straight. And this happens to be, heading toward the tangent line. Anytime you zoom in on a particular point, and while we will talk about what this means later, if it is differentiable at that point, you will see it looking like a line. And in fact, you may want to take a little moment to think about how computer programs create these graphs in the first place, because they sure don't do it theoretically. I'll leave it there. All right, going back over to the notes. Why aren't you moving? I'm having lag again. Thank you. I suppose when too many people are using the internet at the same time, it creates lag, as many of you are experiencing. All right, this is the second definition of slope of a function at a point x equals a. While it may seem like there's not a need for a second definition, there is. And let me also say that when any language has more than one definition for a particular word, it's a really important word. So let me explain this definition. And I'm going to try to keep both of these showing. A is, again, a particular x coordinate. And come on. Okay, I will have you go there. And now you will listen to my pen. X coordinate A is the same as x coordinate A before. We're trying to find the slope of this red tangent line using the blue secant line that goes through point P and point Q. The big thing about this definition is it is using this distance h. H for horizontal distance. Appreciate that you're using the letter H and not having to use delta x. If you don't know, delta means change in something. And a change in horizontal would be a change in x or delta x. A lot of textbooks use delta x. This one uses h. That's going to save you wrist pain in writing out these limits and solving them. But just remember, h is horizontal distance. Now, the x coordinate of q is whatever number a happens to be plus this horizontal distance. And realize we can look at the limit as h approaches 0 from the right side of 0 and the left side of 0. So we do get two one-sided limits out of this. The change in x is just h. The change in y is the function value at that a plus hx coordinate minus the function value at a. Let's do an example. Hopefully you've had enough time to write that down. It is in your textbook if you didn't. We are going to find the equation of the tangent line of this lovely hyperbola at the point 3, 1. I'm going to move that back over here. And then I need to come over here and select something else so that it doesn't see my mouse. All right. Using this second definition, it always starts off like this. Let me point out to you that the number a is 3. So I'm going to find f of 3 plus h. Plugging 3 plus h into that x gives me 3 divided by 3 plus h. Then minus f of a is 3. We happen to already know that number. So that's giving me 1. Or if you like, I can plug it in over here and you can see 3 divided by 3 by plugging it into the function. I'm going to put it back as 1 because it's easier to work with. The first part of you finding the answer to example 2 is just setting up this limit that will find your slope. Next step, solve the limit. I need my common denominator. You have to keep writing limit. You may not want to, but you're going to. Again, it's a rite of passage for all calculus students. Now, for the numerator's fraction, it has the common denominator 3 plus h. And then subtracting the numerators, make sure you put a parentheses as you subtract. I didn't mean to erase the entire line, but that way I can write over here to the side. You can see that we get 3 minus 3. And then continue distributing the negative sign through to get a negative h over 3 plus h, and then divided by that h just to make sure you are clear. A little bit of color coding to help you out. Now, that little over there with the 3s, not a major kill. The real kill is the 0 over 0. That's what we are trying to get rid of in order to solve the limit. Because again, when it's 0 over 0, it is called, anyone? What's 0 over 0 called? Woo-woo! Indeterminate form. And then these h's are going to cancel. Canceled way too softly. Hold on. These h's are going to and that will leave me with a negative 1 over 3 plus h. Now I can do direct substitution and plug 0 into h. Keep in mind, we just killed a hole in the graph of this really lovely function. And this function is identical to that previous one, except that it has a filled in hole instead of a hole in the graph. Anyway, plugging that in, you should see that we get negative 1/3. If you look over here at the tangent line, that looks like a very reasonable answer to slope. The last thing is, let's write that tangent line. I'm going to write it quickly and move to the next problem. So y minus the y coordinate is 1 equals slope times x minus the x coordinate, which is 3. Tangent line, done, leave it. I'm going to move. Boop, boop, boop. Linear motion. Know that while we are in first semester calculus, we have a single variable. It's time. And I can only get one answer for position out of time. That means you are stuck moving back and forth on a line. Now, I wanted holes that filled in, but I gave up on trying to figure out how to do that in this particular program that I'm newly using. But All you're doing is moving back and forth on a line. It's terribly boring. That is every movement while you are in AB is referring to that. In order to get two-dimensional motion, in BC, we'll work with parametric equations so we can get an X and a Y out of a single time value. But until you reach multivariable calculus, you're very limited. I want to point out this picture right here. When we talk about the graphs of our position functions, we're going to see something two-dimensional. You need to understand this is using time as a physical dimension. This is not the path. Anytime time becomes a physical dimension, what you are viewing is a warped view of whatever motion happened. But we need to do this two-dimensional graph because if I were graphing the actual motion, it would look like this. I start here and then I go here and then I go back and then I go here and I stop right there. See? Perfectly clear. I'm going to erase that so that I can then continue using these things. So this is a big physics application that we use in calculus. It will be on the AP test. This is one of the most important applications that we have. Displacement is a physics word, and it's a directed distance. We'll talk more about it as we go along because we're going to continue to talk more about motion. This is an introduction to it. Know that we're going to call it the position function, even though it's representing displacement. And for those of you that don't have a physics background and you don't know what displacement means, for now you can just think of it as distance, but it's distance where you could have a positive or a negative. So when you're dealing with position on a number line, that number line needs to have a zero position. It also needs to have a positive side and a negative side. In calculus, we stick to the math directions that have been predestined already, as right is positive, left is negative. So I've got a positive one over here and a negative one over there. And hopefully you can't hear the outside noise. Oh well. Now, I'm going to place these two just in a couple of places, and I'll just pretend what their numbers are because I don't want to create an entire number line. Looks like this is maybe at x equals 2. Let's say maybe this is about at x equals 3. If this is my initial position, now I've got to say, I'm sorry, I apologize. We're going to use the letter S for position. So if this is my initial position, I'll put S not snot. And then my final position, I'll put S sub F for final position. If I am looking at displacement, then I am looking at the change in my position over the change in my time. Now the change in my time, oh wait, I didn't give you time, did I? Let's pretend that I am located in this position at time 0 and that I'm in this position at time 2, and I'm going to put some units on it, seconds. In order to get positive time, I need to make sure that I take the final position and subtract from it the original position. And I want you to see that we are getting I'm actually Sorry. I'm moving on to something without saying I was moving on to it, which is something I'm really, really good at doing. I actually started looking at velocity. I was initially intending to just present this, but I started going somewhere else while I was at it at the same time. I want you to notice that this change in displacement is a negative number. Displacement is basically a location where you are maybe currently at with respect to a location that you were previously at. Now, if you're just given a number and told displacement, it's probably looking at what is your position from zero. But position based on, am I on the positive side or the negative side? So if you travel in the direction of negative, you're going to get a negative displacement for that time period, and that's going to give you a negative velocity. Velocity is change in position over change in time, which you can probably see down here. Now, if I had my initial position be this one, and my final position be this one, you should see that that would end up giving me a positive displacement and a positive average velocity. You need to know that when you have a positive velocity, that says you are moving in a positive direction. And for first semester calculus, that just means if you're on a horizontal line, you're moving to the right. If you're on a vertical line, you're moving up. And then if the velocity is coming out negative, you're moving in whatever is considered to be the negative direction. Now, why are we using S, not D? Physics uses D. Why can't we use D? It's because calculus has this lovely way of writing derivatives. And I'm going to say a derivative that means the derivative of the y function with respect to x. We will write it as dy over dx. D for derivative. Yeah, that takes over distance. Derivative in calculus is a bigger word than distance. It gets to take the d. It would be poorly written to say dd dt, because then these d's have a different meaning from that d. That's why we have to use a different letter. We're using S for position. You can look up where that comes from because I don't remember off the top of my head. So moving along, average velocity is slope, change in position over change in time. But what is instantaneous velocity? Now, first of all, I want to say that if I am dealing with instantaneous velocity of f of t at time a, then my instantaneous velocity is defined as the limit as time approaches a of the change in position over the change in time. This is based on definition 1 that we went over. We could also write instantaneous velocity in terms of definition 2. I'm writing it this way to show the correlation between average velocity formula to instantaneous velocity. If you are asked for average velocity, you're not doing a limit, you are doing a slope formula. If you're asked for instantaneous velocity for the next 2 days, you're going to use a limit formula. After that, you're going to use derivative formulas. And you can look at the examples in your textbook. I have shown you one example each of using definition 1 and definition 2. Know that the textbook is going to ask you to find slope, or maybe it'll say instantaneous something. It will tell you using definition 1 or definition 2. So just be aware of that. You need to use the two definitions separately at separate times. Also, just to point out to you, officially say tangent line 2f of x at x equals a. When you write the equation, make sure that you are writing y minus y coordinate equals slope times x minus x coordinate. On the AP exam, when this shows up, you are filling in 3 spots with numbers, and you have an equation of a line, and you stop there. Do not feel the need to write it in mx plus b form. So again, I'm going to skip these definitions, and I'm going to come over to this examples, and I'm going to come over to this word problem. And let me check the time. I want to make sure to give you maybe 15 minutes for the quiz, at least 10 minutes for sure. This is the last thing to go over. So you can see this is a bit of an old problem since none of you were born during this time frame. It wants you to interpret and estimate the value of d prime of 1990. Woo, mighty class of 90. Sorry. I graduated high school in that year, and I just dated myself. So anyway, as far as interpret, this is very, very, very important. It's important to understand what derivative means in the context of a situation. Now, laugh at this. Please laugh at this. The U.S. national debt at that time was put into billions of dollars. I remember when it was billions of dollars, and I thought, no, that's terrible. And now I see trillions, and I'm like, okay, so first of all, for how do you need to explain in words what this is telling you? Before you start writing it down, what I recommend is you figure out what are the units of the function you are taking the derivative of, and what are the units of the input variable that you are taking the derivative with respect to, because I could change who I decide to look at the rate of change of national debt with respect to. But I need to keep going and focus on this. So unit of d over unit of t. Be careful. The word time is not a unit. Look around. What is the time unit being used? Woohoo! And what are we using exactly for the units of d? Billions of dollars. So when you explain the meaning of d prime of whatever year, you need to make sure that you state that it is giving you billions of dollars per year. Okay, there we go. So, you know what? I am running out of time, so I'm just going to have to leave it with verbal words. It is the rate at which the U.S. national debt was, the rate at which the U.S. national debt was changing in billions of dollars per year in the year 1990. Now, I've got d prime of 1990 and 1984. Why did I use 1984? Some of you are going to read that book this year. Some of you read it last year. And I want to point out to you the difference of expectation on the AP test. On the AP test, if they ask you to find an estimate of a rate of change at a particular time, and that happens to be one of the times in the table, do not do more than one slope. Your textbook is going to do more than one slope. Don't listen to it. Your options are, you can either look at the change between 1995 and 1985, or you can use 1990 with one of its two closest times. Where's the other one? Lag. I experienced lag time. Again, too much internet when the internet just can't handle it. Someday your children are going to be like, what? Your internet couldn't handle all that? 1995 minus, where was I? There we go. Okay, to not waste time, I'm just going to explain. You're going to put in these y values, subtraction of the ones that go with the times. Okay, do one of them. Don't do all of them. And I am fine with that on your homework to do just one of them. If you are given a time that is not included, then you have only one option. Provided you can tell where the year lands. You must use the nearest two points of data. If you're being asked to estimate something and you use data points that are further than ones that you know, are you being reckless, careless? Or, you're basically, know that they expect you to use the two nearest points. If you don't, you are wrong. So when you estimate for 1984, you must use the years 1985 minus 1980. And then I'll go ahead and write just this one out. And I'm going to assume that you understand how to write the numerators of these three. And again, those are how you can approximate, oh yeah, squiggle equal for approximate. D prime of 1990. All right. Now I need to get you going on the quiz. So I hope you enjoyed derivatives. Your homework is up. Woohoo! I'm going to stop